Hi, I'm Fabrizio Schiano, and the work I will present at ICAR 2018 is the fruit of a visiting period I did during my PhD at Boston University under the supervision of Professor Roberto Tron. The results we achieved during this work were extremely exciting because we were able to look at the problem of localization of a group of quadrotor UAVs through onboard camera measurements. The problem of cooperative localization is the one in which each robot of the group has to be able to reconstruct its pose, which is in the special Euclidean group SC3, with respect to the other robots of the formation. One way of solving the localization problem is to use concepts from the theory of rigidity and then ensure that the formation is rigid. However, earlier results based on rigidity from camera measurements were able to estimate the relative pose of the agents only up to a global scale factor of the whole formation. Instead, in this work, we showed that it's possible to solve the localization problem without having the scale ambiguity. This was done by using concepts of rigidity, but taking also into account linear and angular velocities of the robots in their own body frames. These led us to the introduction of the novel concept of dynamic bearing observability matrix. This is why in the upper left of the video we show two plots with the last 8 singular values of this new matrix on the left and the last 8 singular values of the classical bearing rigidity matrix on the right. These told us that the dynamic bearing observability matrix has a null space which contains one vector less than the bearing rigidity matrix. This made us understand that the scale of the formation is indeed observable. Therefore, we designed an extended Kalman filter to estimate the full pose of the agents in order to validate our ideas. In this video, we show an experiment involving two real quadrotors which are estimating their pose with respect to a virtual agent which is fixed on the ground. On the upper right of the video, you can see the plot of the true versus estimated distance between the two flying robots. You could also notice that after taking off, the two robots started flying around in order to estimate their pose with respect to the virtual agent. It's important to notice that there is not any kind of active estimation strategy, and therefore the robots are performing a pseudo-random trajectory, hoping to excite the variables they want to observe. From the plot on the upper right, you can notice that while flying, the robots are able to retrieve the real distance between them without any distance information.